an overview. Yes, recording in progress. Got it. Good. Yeah, an overview a little bit on the traffic simulation research at VTI, but I'm also affiliated with Linköping University on 30%. So this is, some parts are mainly at VTI, some is in relation or connection to Linköping University as well. And then it's VTI Linköping University have that collaboration with Nagarjun and Hanin and Jongji and other colleagues there. So, but a little bit of overview, but then focusing a little bit on two application areas, which I think is maybe you don't hear that often about. So 2+1 roads for rural roads and bike traffic simulation. So the agenda, I will tell a little bit short about me, and for those that don't know what VTI is, I will give a short introduction, but the focus will be to give a short overview on traffic simulation development and application at VTI and LIU, and then focus on these two application areas, traffic simulation of 2+1 roads and simulation of bike traffic. So I'm starting to getting old. I was born in '79 and I moved to Norrköping and studied Linköping University in '98. In the Master of Science education, it was quite new then, communication and transport systems. And after that, I continued with as a PhD student shared between VTI and LIU. And that's a way we have for several PhD students that they have employment both at VTI, which is a research institute, and LIU and the university. So both being present in the academic world and in the research institute. And I finished in 2009, and on the PhD, the topic was using microscopic traffic simulation to simulate the surrounding vehicles in the driving simulators at VTI, which is another field which been developing driving simulators and apply them at VTI since I think the 70s. In the beginning, they had to build their own graphic cards and so on. Now it's more using available softwares and hardwares. But yes, it's one area there. And then today I'm a senior research leader at VTI and associate professor at LIU, and focusing, as Nagarjun said, on traffic simulation and analysis of transport systems. So not only traffic simulation, we also do some capacity analysis and kind of highway capacity modeling for intersections and so on. But lots of focus is on development and application of specifically microscopic traffic simulation. I have other colleagues working with mesoscopic and DTA and so on. And VTI, for those that don't know it, in some sense, it's similar to TNO. It's probably the most reasonable, similar in the Netherlands. So it's a research institute. It's commissioned by the Swedish government, but we don't get the funds. We get some funds directly from the government, but most of it we have to apply for research funds, either natural research funds or international ones, as the Horizon and others. And we are directly then under the government and under the Ministry of the Infrastructure. So in the same ministry, we have the Transport Administration that runs the roads and the rail traffic, the Transport Agency that have all the permissions and driving licenses and so on. And then we have some other paths here under the ministry. But VTI is a pure research institute, so we are kind of strange. We don't have the official task for us is to provide research and knowledge to the Swedish transport area. So Swedish Transport Administration is one of the main sources of funds, so we apply for different calls, for example. Yes, so traffic simulation at VTI, there are several different areas. I try to put some of them here and since we'll share the slides, here is also links where you can contact if you're more interested in, for example, variable speed limits or connected traffic signals. You can talk with my colleague Ellen Grumet, which wrote her PhD on variable speed limits and the possibility to use connected vehicles in variable speed limit systems. There's also a current PhD project more on bus terminal and station simulation. So how to design which bus to stop at which station, and how the delay look at the bus terminal where you have several potential stops. We have Fredrik Johansson, which made a PhD on pedestrian traffic simulation and are finalizing project on how to calibrate pedestrian traffic simulation models. We have several projects in the past and then also now on simulations of ADAS, advanced driver assistance systems, and automated vehicles. So one is the PhD project by Ivan Postigo, which is the one where we have the collaboration with Nagar Yund and colleagues. But there are also other EU projects like the Coexist project, and there's upcoming project on augmented CCAM and other things. I will tell you a little bit more on that. And then we have the start of traffic simulation at VTI in the 70s. This rural road traffic simulation. Swedish is a long country. Lots of the road kilometers are rural roads. So already in the 70s, they started to develop event-based traffic simulation models. So I will tell you a little bit more on that. And we also have this bike traffic simulation track with a PhD student called Guillermo, which me and Fredrik are supervising. So I will not talk more on the traffic control applications, a bus terminal or pedestrian. I will give a little bit on the traffic simulation automated vehicles, but since there are so much presentations work on that, I thought it could be nice to talk about something else today. So the focus will be on the rural road simulation and the bike traffic simulation. So some short about the simulation of ADAS and automated vehicles. I think it's interesting because it's kind of taking microscopic traffic simulation out of the comfort zone. It was developed to simulate human driver behavior without ADAS or automated vehicles, and mainly in order to study different road designs or traffic controls. So when we add driver support systems, one thing is that we need to add the system itself to the simulation, but it might be that it gives advices, or it might take over control of some of the actions of the driver. So we also need to add the driver decision modules. It could be to what extent the driver comply with advice, if it deactivates the system, reactivates, and so on. It might also mean that we need to model the vehicle dynamics a little bit more and kind of keep track of the vehicle state in order for the driver to model the driver support system properly. One such example I took from the EU project ecodriving, where we work together with some of the TNO colleagues like Jadine Klunde and Isabel Wilmek and Martin van Noot, where there was development of different types of eco-driving systems, giving guidance to drivers. They were implemented and tested in field trials, and then we developed a simulation framework where we both included the system itself, but also driver model that reacted to this speed and gear advices by the system. And since this also gives gear advice, we also needed to add a simple vehicle dynamics model and a simple modeling of the powertrain. And in this case here, we built it as an application programming interface because we use different simulation programs for different settings. So we used one for a rural road in TNO. They used one for motorways, and in Leeds they use Aimson for simulating urban streets. So different simulators here, but of course it could have been included directly in the simulation program as well. But I think this was kind of the first steps towards what we are more in today, which is maybe that traffic simulation of drive support systems is maybe not obsolete, but it's more focusing now on the traffic simulation of automated vehicles, with the problem that there are some data on the first generation of automated vehicles. It might be difficult to get their hands on it because it might be OEM properties and so on, or it might be more research tests. But for sure, we don't know how the automated vehicles behave in a couple of years, and the transition period will probably be long, or at least that's my guess. And I think there are several others that think that will take some time. So how to deal with that if you would like to investigate the potential impacts on traffic and traffic flow dynamics. One solution that we worked with in this Coexist project was that we tried to look on potential different paths on the development of the behavior of automated vehicles. So we developed 4 different conceptual descriptions, one being more kind of safety first, and in the other end it would be an all-knowing driving logic that have perfect knowledge about everything and can act from that. And then we also made scenario-based analysis and look on the potential range of effects, since there are large of uncertainties. Maybe you already see this, but this is the different logic. So the first on top is what we call rail safe, which is this kind of minibuses running on a predefined GPS tracks, and they have to stop and they cannot decelerate more than maybe 1 meter per second square, because then the unbelted passengers would fall and hurt themselves. The cautious logic here is a more normal car that will try to drive in such a way that it will never be in an accident, which means that it has to apply quite long time gaps. The normal was idea of saying, okay, something like a human driver behavior, but with maybe parallel perception, shorter reaction times, but maybe with more limited possibilities to know what happens further ahead, where an experienced human driver could maybe do better. And the all-knowing was this, in principle, fully connected knowledge about everything around it, so it could try with very short time gaps. In the PhD project by Ivan Postigo, we applied these logics for a traffic simulation of a motorway in order to look on the potential ranges of the effects. And this here is then for the throughput at the end after an on-ramp. There's lots of different potential mixes here of the cautious, normal, and all-knowing logics, and for different penetration rates. So 0 here, then it's 100% human driven, and then 20, that means that it's 80% human and 20% automated at lots of different mixes. And what we can see here is that quite large range, and this kind of cautious behaviors will have an impact on the throughput, but also even at lower demand levels. I don't have the figure here, but it will also affect and increase the delay already at lower levels, demand levels. So this expectation on that automated vehicle will solve everything, probably you know it as well, and then I heard it from others that maybe that's not true, or maybe that's need to be overcome some of the potential deficiencies. On the other hand, we can also think about that it's nice to have increased safety by a cautious driving style, which might reduce capacity, and that would probably be the case also if all human drivers would keep the gaps that they would need to be safe in every situation. So it's also this kind of balance between safety and efficiency, which maybe is not discussed so much today because, yeah, depending on if as a traffic planner at the municipality or the road administration, you are quite keen on getting a good capacity, and maybe you don't like to offer that one to increase safety all the times. But that's all about automated vehicles for today. And I thought then, no, sorry, I had one more slide. I forgot about it. Of course, I should mention the collaboration paper, state of the art, and looking on these aspects to consider for automated vehicles. So this is the collaboration work with Hanin and Nagarjun and Narayana and Zhongxi. So that's under review. Hopefully it will be accepted, the reviewed submission we did for the IEEE journal. So I will not talk about more it. If you're interested, I think Nagarjun or Yongxi or Hanin will be happy to explain it for you as well. Yes, so rural road traffic simulation. Maybe to some extent for Netherlands, I mean, there are very short distance between the cities in the Netherlands compared to Sweden, where we have long. So in some sense, maybe this is exotic for you. I don't know, or maybe it's of less relevant. But I think it's interesting. And actually, one of the co-authors of this works is no longer at VTI, but Andreas Tepani. He went to Delft during his PhD and also had a collaboration together with Gertje Hegeman, I think, if I remember right, on traffic simulation, rural roads, and overtaking. So there is a connection here as well. Yes, as I said, this started in the 70s at VTI, and we have a rural road traffic simulator called RuTSim. Main reason for this is that at least when starting, the commercial models and the open source models available then were kind of one direction traffic. Now Sumo, Aimson, VISSIM starts to have also oncoming traffic. So it might be a less need to have our own code because of course you need to keep track on it. But it's a model for rural highways where we have effective road geometry, interaction between oncoming traffic. If we have this kind of single carriageways, 2-lane roads, but also in the last 20 years since this 2+1 roads starts to be built in Sweden, there's also an interest to know on when we have the barrier between the oncoming lanes, how will that affect the traffic performance. So as you see, it's not a very fancy graphical user interface or visualization. So for sure, it could be good to put it in some of the more advanced traffic simulation softwares, but it do the job in that sense. And what is a 2+1 road? For those that doesn't know, it's in principle the idea was that if you widen the road a little bit, it might be too expensive to build the motorway, but you can widen it. Or if you have a wide road, you can, in principle, have 3 lanes all the time and let the middle lane vary between the oncoming directions. In Sweden, we call it 2+1 road. There are sometimes called Super 2 highways. In the US is kind of a similar but different, and 2-lane expressways in Japan. Sometimes it's more that it's 1 lane in each direction and then some overtaking or passing lanes. The Swedish one is really the thought that in general it would always be 2 lanes in one direction. Of course, there might be intersections. It might be, as we see also the transition from 2 to 1 lanes takes some of this area. So in principle, it's only kind of 45% of the length that's 2 lane in one direction. But you could also have sometimes less than 40% to 2 lane segments. So the idea is that we have, or there will be a queuing going on the one-lane segments, and then when we get to the two-lane segments, it's overtaking possibilities. There's a sign telling the drivers on how long the segment is. There's a sign telling when it's 400 meters to the merge, and then there's a sign where it's a merge. And also information on how long the upcoming one-lane segment is. So there's quite a high desire to overtake, and it's not kind of that you go out in left lane and just pass, but it's really like on a two-lane highway and with the oncoming traffic where you actually accelerate and increase the speed quite a lot. And there's also frequent merging at the end, which is different to some extent to a merging at a lane drop or on an on-ramp. So to model this, we need to first capture the free vehicle speed adaptation with a curvature and slopes and so on. Of course, we need car following as in any model, but we need to model more importantly than the overtaking decisions and the merging maneuvers. One of the things that differs from rural road simulation compared to the motorway or urban road simulation is the speed adaptation. So here as for motorways or urban roads, we consider the speed limit and how the driver complies with that, but also the curvature and the road width. And although the empirics might now be quite old, the idea is that you have each driver have a basic desired speed, and we have a distribution of the basic desired speed, the speed that the driver would like to drive at, where there's no speed limit or a straight road and it's wide and so on. And then we reduce this speed, but it's not only a reduction, as you can see, is the red curve is also kind of rotated or tilted. So it might be that for some of these things, the fast drivers are affected more. So in a curvature, maybe there's a safe speed to go through, and independently on how fast you would like to drive, maybe all the drivers need to get down to that. So the effect on the desired speed through the curvature might be larger for those with a high desired speed, those compared to those that have a low. The other part is the slope, and here the approach in RuTSim have been that we look on the power weight ratio. So especially for trucks which might not be able to keep their speed in the uphills, the available power in combination with the weight is important. But also, of course, air and rolling resistance and the slope with the effect. For car following, we are basing our work on the IDM. We did some adaptation to it. I will not go into details, but of course, one could probably use any car following model here, which you think is good. This is mainly interesting from the one-lane segments, but also, of course, for deducing the deceleration needed to merge into a gap. So the more important part is the overtaking and merging process, and here we divide these two-lane segments into 3 different areas. So the first one is kind of the overtaking area. So sorry, that should be that it's 700 to 2,400 meters. That's the total length. I wrote it wrong. And when a two-lane segment starts, there's either the blue vehicles already following the orange vehicle, and then commonly they will start to overtake if it's not completely full with vehicles. If the orange vehicle is a little bit ahead but clearly slower, the blue vehicle, what we've seen in observation is that it's already increased the speed, so kind of I need to catch up and overtake before the end. So there's kind of a desire to increase the speed to overtake. And then when getting to this merging zone, the decision is more kind of, since it's an overtaking process, the decision is what's easiest to merge in front of the vehicle that I'm currently overtaking, or should I take one more because I have so high speed, so it's easier, or the deceleration that needs to be applied is smaller. So in the first one here, it's depending on the length and how much traffic it is in the left lane and the desired speed of the red vehicle here. Then the decision is there, and also in order to capture that it's not only switching lane and then passing, we have a temporary increase in desired speed for the overtaking vehicles, which is then a calibration parameter. And then when the red vehicle here is side by side with the blue vehicle, there's a decision whether to go back or continue overtaking more vehicles when they are in. And for going back, it's in this area here, it's looking on the car following model and the side gap, while when we get to the merging zone, then in the first, it's the side gap, that's what we're looking for, but in the second zone, it would be accepting smaller gaps or higher decelerations. And here we have a gap choice modeling based on the models from HEDAS in the Artemis model. Slightly different because here the red vehicle would, in principle, never consider to merge behind the vehicle it's currently overtaking, at least not if it's side by side or partly passed. But there's also modeling on the courtesy deceleration of the vehicles in the right lane. And then the last, it's really a merge, and here there could be both in reality and especially in the model, maybe in the model too much. We are lacking a little bit of calibration data, but it's a lot of deceleration happening here because the vehicles in the overtaking lane commonly have a quite high speed and would like to pass, especially cars passing trucks. Yes. So some example of trajectories of a simulation in RuTSim. We have the blue part here from 0 to up to 2,300. This is one lane segment. We can see the blue trajectories here commonly decelerating and getting into following. And at the start of these two lane segments, there are lots of accelerations and overtakings going on. In this case here, we could see a decrease in speed of the trucks, the orange lines, and that's due to that there's an uphill at that part, so they're actually slowing down a little bit more. And we can also see here that there are lots of different decelerations going on at the end of the merging. Another way of looking at this is, of course, to look on the average speed and the confidence interval. A problem we have is that for rural roads, there's not as much measurements as for motorways and urban roads lying around. So previously we have calibrated based on tube measurements that give you the average speed and flow on the hourly level. But now we have a new test stretch where we are testing this, where we have some travel time data from Inrix, so that's giving some information, but it's also difficult because it's not matching the 1 and 2 lane segments perfect. So we are also having a collaboration project with a company called Viscando, which do traffic measurements with video. So we have put up then 6 video cameras that collect trajectories of area 50 meters each or something like that. And the work now that Viscando is working on is to recognize the same vehicle at the different locations. So they have pictures from the first sensors and they have pictures of vehicles on the second sensor. And then with the image recognition and putting different points here on the vehicles, they would then try to figure out which vehicles which. And from their interest, they are doing this independent on which order the vehicles pass. Then of course they can use the time windows in order to kind of limit the number of cases. But this is ongoing, and we hope then to also get some information on what's happening in between the areas of the cameras. So when we get this, then we will go back to do calibration. But what do we apply this for? We have applied the traffic simulation for looking on different road designs, kind of traditional consultants work, but we also did a couple of years ago a study where we tried to look on what is the optimal length of the two-lane segments. So in principle, we can say that there we can have short or long passing lanes, which also, of course, if we have short passing lanes, the one-lane segment will be shorter. If we have long passing lanes, the one-lane segments will be shorter, since it's going back and forward from the two different directions. So there are different pros and cons. Every merge is in some sense a bottleneck. So if we have long passing lanes, there will be fewer bottlenecks, and we can have several vehicles pass on each. And short passing lanes, maybe it becomes more kind of overtaking trucks, or maybe it's difficult, or that the overtaking tendency would be lower. So there's pros and cons, and we were interested in investigating kind of, is there an optimal length? So what we did was that we designed a road where we varied then the length of the passing lane. We also looked at different passing lane shares. So as I said, 40% would be kind of, there's always 3 lanes in both directions. Sometimes we have roads where you have less shares due to different reasons. We also looked on different heavy vehicle shares and at different vehicle flows. We presented this with the average travel time per kilometer, so kind of the inverse speed. There we also looked on other metrics. We have the blue dots here, sorry for the Swedish text, but the blue dots are for 9% heavy vehicles, and orange for 12%, and green for 15%. And then we have the different lengths, and to the left here, we have for the 20% share, middle 30%, and to the right 40%. And this is for the lowest flow. And then if we increase the flow, of course, the travel time per kilometer would increase, but we can also see that the difference increase. And independently, more or less, on the flow, we could see a trend that it's not obvious that longer length is better, because the longer one gets, the longer also, of course, the one-lane segments get, and the more vehicles are catching up with each other. So according to this, it seems like optimal length around 1,000 to 1,400 meters. But this is also, of course, a very hypothetical scenario, because here we don't have any intersections and so on, and there might be lots of different reasons why you put a certain length due to how the road goes and the distance between intersections, and where do you have a uphill, because you would prefer to have 2 lanes in the uphill direction at that point, and so on. So it's not always that you can choose. But one interesting thing is that this can be compared to some extent with the idea of the cycle length in the traffic signals. In the traffic signals, we know that if you have a long cycle length, you can get larger capacity, but also means that if you have a long cycle length with the same split of green and red time, there's more red time that you will queue up vehicle, even though it's more green time where you can discharge the vehicle. So it's in some sense a similar kind of shape. So I will switch to the bike traffic simulation. I think we should almost finish now to get some more questions, but so I don't know if there's any questions here already on this one that we should take before we go to bike. So in the first one was which microscopic simulation model. So that's I think I said then it's a research code that we have at VTI put in C++. For the other one, how far upstream of the lane drop the driver starts to switch lanes, and that could be very late sometimes, and sometimes they crash into the cable barrier. So that's also a safety issue, of course, even though the safety gains of these types of road they're almost as safe as on the motorways. How far downstream the lane drop is traffic flow home easy? Yeah, that's also a good question, because there are when high flows and lots of heavy decelerations, there takes some time before you stabilize on the one lane segment. You get the speed dropping more before it's kind of stabilized again. And that's also one of the things we would like to study with these cameras, because the cameras also look on the other direction. So we'll also have the start of a one lane segment in the other direction.
Johan, thanks for your answers on my questions. So we're currently trying to gain insights on the effects of lane drops ourselves with some drones. We flew over a couple of those lane drops to try and gain some insights on turbulence around those lane drops. I was wondering if we could compare some of our results based on your own research and calibration.
Yeah, that's for sure interesting, even though a lane drop on a road where it's kind of have been two lanes and more kind of you can switch lane and pass is slightly different. But we also discussed for this case if we should have a drone, but its problem is that we would like to capture this kind of 2 kilometer stretch, and the drone can maybe only capture the last part and then only for a short period. So we use the cameras here, which is kind of shorter distance, but there's a 1 week of data, so it's you never get what you like.
We captured for about 1.5 kilometers.
Okay, yeah, you had several drones, or
should look into that, but perhaps we did, or a very large angle of camera.
Okay, yeah. No, but that's for sure interesting. So please drop me a mail, and then we can have bilateral discussion on that.
Yeah, thanks.
Yes. So a little bit on bike traffic simulation. This is a PhD project by Guillermo. I'm the main supervisor at LiU, and we also have a colleague at VTI, Fredrik Johansson. And he started almost 1.5 years ago. So it's and we do 4 years plus 20% teaching, so it will be 5 years. And so it's started a little bit, and that's the first on bike traffic simulation. So there will be preliminary work and results for that. So background is more kind of, yes, we had development of car microscopic traffic simulation models since the 50s or 60s when General Motors started, but for bikes it's kind of lacking model support. I know you have colleagues there in Delft looking a little bit on the bike traffic, but and there's something in Wuppertal as well, but it's still kind of many years behind the car traffic, and even also behind pedestrians, because pedestrians, there's been quite a interesting works on evacuation, also on the congestion at bus terminals or a train station and this kind of things. So the purpose is that we would like to investigate, develop, and evaluate simulation models for cyclists. And here there are some similarities for cyclists to the rural roads, which I think is interesting, maybe more to some extent than for the motorways or urban, because we don't only have the interaction with other cyclists or other road users, but also with the infrastructure is very important. We don't have a speed limit that use the desired speed of cyclists, more on the width or the curvature or other parts or the slope. So why should we model bicycle traffic? Yeah, to some extent, it's maybe there's a lack of model support tools because the congestion and the effects have been more limited. Although in the Netherlands there are for sure some congestions, and there are in Stockholm and Gothenburg in Sweden as well. But there's also a high desire to increase the share and the number of bike trips. So if the goal of the municipality would be achieved, then they would have for sure much more congestion and need to deal with it. So let's develop the tools as fast as possible. That's kind of the idea, in order to support the planning and evaluate how changes in the traffic system affects traffic performance for cyclists, which is maybe not even calculated or estimated that much today when we do changes in the traffic system. So in principle, it's a similar approach. We model the individual entities. It's not that bikes have not been simulated already today, but in principle, they are either simulated using the car following and lane changing models of car-based traffic simulation, or they're modeled as fast pedestrians using these social force models. And I mean, bike and bicyclists are not a slow car. They have more degrees of freedom, but they're not really fast pedestrians either. So there might be a need to look on how they should be simulated and to what extent those approaches can be used. And as I said, the infrastructure might have a larger effect, and maybe cyclist is the most heterogeneous type of road users. For sure, more heterogeneous than cars. With the children, old, elderly, fast running cyclists, and so on, maybe even more heterogeneous than pedestrians. So for a microscopic traffic simulation model of bikes, we need to consider the free riding and interaction with the infrastructure, of course, interaction with other cyclists if we're on the bike path. If we're on a shared path with pedestrians, we need to consider them, and in intersections or when running on shared street with cars, we need to focus on interaction there. And it's impossible to do all this in one PhD, so we started with a project where we focus on free parts here, the free riding, cyclist interaction with each other, and the interaction with the infrastructure. So kind of waiting with intersections and interactions with other road users. So one thing, sub-project for Guillermo is looking into the effects of slope and the gradient, and how could we model that, both in terms of that it has a negative impact on the uphill, but also that it might be that you have a change in the side speed on the downhill path, because it might not feel safe to use the gravity acceleration fully. The second part is that we will look into the characteristics and the heterogeneity on that. How do the preferences of speed and lateral position and so on look like? And the last one is here on the cyclist interaction, so overtaking and following behavior and so on. So the scope here is that we limit to bike path segments, either bidirectional or one directional, but in principle exclusive cyclists, or maybe we'll have some where we'll be shared with pedestrians. There are also sometimes pedestrians walking on the bike path, even they shouldn't. It's focusing on the tactical or operational behavior, so route choice and other parts and strategic level is not included. We are focusing to look mainly on high flows and delays due to that, and which types of bike users. That's kind of limited to the data, but the aim is to represent the heterogeneity. For this, we need data, and again, here we are focusing on video-based data, either from drones with the manual tracking from this software T-Analyst. We also tested some of the commercial versions, and we also looked into data from this Viscando systems that I talked about for rural roads. So the good thing with this is that it's a fixed camera and you can track for a longer time period, while the drone is maybe capturing a longer distance, but it's still extracting trajectories of cyclists is more difficult than cars apparently. So there's no perfect tool yet, and then also the GDPR and the surveillance legislation is a problem, so you can kind of film and save the movie. So in the Viscando system, for example, you can get this kind of anonymous video out there, but you cannot get the real video, because then it might be possible to see who is moving and so on. For the drones, it's easier in that sense because it's so high up, so it will not be a GDPR issue in that sense. So we have 4 different data sets. The first one is a bidirectional path in Stockholm, one of the highest flows on a bike path there. In total, it's almost 46,000 trajectories. In a later collection we did this fall, we did another place in Stockholm on Norrmälarstrand. It's also a bidirectional path. The good thing here is that we also realized that the wind is quite affecting the speed, so we would like to at least be able to control for it. So we also had some wind measurements there. The third data set is a drone data set for an uphill and downhill paths. It's a little bit longer distance, but in that sense, it's manual track trajectories. So there's much fewer, because of course it's also a shorter time period that the drone can be up, or if you don't go up and down several times. There's also a little bit collaboration there with the Lund University that did part of the measurements. And then we have some cross-sectional measurements at various locations from 2018. And although you can get the trajectories, it's still independently. If we look from Viscando or data from Sky or and so on and others, we talked with the people from Wuppertal, it's kind of the automatic tracking for cyclists are not perfect yet. So if you would like to have it perfect, you have to do it manually, and then it's very cumbersome from that point of view. So you get some ghost trajectories, you get some problems where tracking the shadows and so on. So in this case, for data set 1, for example, it's kind of 60% of the trajectories that is useful, and then 40% of those is on the peak hours. So it's still quite a lot of data. Here we also removed trajectories that are okay, but that are disturbed by those that are strange, because if you like to look into interactions and so on, we don't like to look into interaction with something that's not the true trajectory or that's a faulted trajectory. Yes, so some of this work, Guillermo started with a master thesis. He tried to see if it's possible to simulate this the bidirectional bike path in VISSIM with a car-based inspired approach, and it was possible to kind of get the speed correctly on the flats before you get to the downhill. But for the uphill, this was difficult to get the right speed and the speed distribution. So the effect of the gradient was not captured in a good way. So the first study he did for his PhD was to look into the gradient effect and how that could be simulated. So we have this data then from 2018. We focus on the morning peak. In VISSIM, the modeling of the gradient is in the car-based approach is that we have the gradient, and then we have what we call the maximum acceleration function, describing the possible acceleration given the speed. There were some calibration of that done by this company Covey in Copenhagen. So we start from that function, and the gradient then is affecting that this maximum acceleration is decreased by 0.1 meter per second square per every percent gradient. So the left here is showing how the function looks in general, and then the 3% gradient case that we have here is on the right, meaning that for some speeds, there will not be possible to keep the speed for the cyclist, so they will go down. And that could be compared to the modeling of the slope in the rural road simulation. And in principle, this is an example of 3 different cyclists at different speeds. So you can see here that those will drive fast. Everyone will end up in the same speed, independently on how fast they would like to cycle on a flat segment. Furthermore, when looking to the speed of the observation here, the black point, and then we simulated different gradients, we can see that it's kind of double the gradient that gets down to the average speed or distribution that we have on the observed. So we can see that up to 3%, there's very little effect on the speed in the simulation. So of course, there's 2 options. One can try to calibrate this maximum acceleration function, and we could also think about that adjusting this parameter 0.1 meter per second square per 1% gradient. We tested both these different approaches. So in top, we have the observed and simulated speed distributions. And then for the simulated, we have it for several different replications, and for the observed, we have it for 4 different days. And approach A, which is kind of where we adjust this to 0.2, or we look on the 6% gradient, we can see that we can capture the average rather well, but the shape is strange. If we try to calibrate the max acceleration function, we can kind of get the shape right, but it's still too high. So conclusion from that one is that a car traffic modeling approach, at least the one in VISSIM, could partly reproduce the bike traffic at flat conditions, but we have difficulties on the slope. And this maximum acceleration function is quite complex. It's not easy to know how to calibrate it. And I think more and more when we talk to others as well, there's kind of a need to develop more appropriate bike traffic approaches in general and not using this car following and lane changing models from cars. Yes, and the next steps, as I already talked about, and we should have some time for questions as well, so I will shut up.
Thanks a lot for the really nice presentation, Johan. So we have maybe time for 1 or 2 questions, maybe. So the floor is open. Feel free to unmute yourself and ask a question to Johan. Tick.
Everyone wants lunch. Yeah.
Yeah. Well, it's 3 minutes for lunch. So.
Yeah. No.
Yeah,
and also, yep.
For the bike simulation, I was wondering if you were thinking in the ranges of calculating watts per kilogram, because that's kind of usual in going uphill with bikes and calculating how that works, and how you would incorporate electric bikes in that, because they have a standard watt, like 100 watts has been delivered standardly. So is that another approach? And perhaps
Yes.
it won't work in VISSIM, but
no, that's really good. And the ongoing, I didn't put it because it's really ongoing. We're running a master thesis and Guillermo working on it. But the idea is that it might be kind of a desired power usage of the cyclist. And it might be that you are, as for the overtaking of cars, you might increase your speed a little bit. It seems like some preliminary results when you look an uphill, that might be that they actually put in some extra power compared to the flat, for example.
Yeah.
So that's for sure the idea to kind of look in, and especially for the uphill. For the downhill, it seems like there's something more happening. It's not only that you get kind of help of the gradient. So there's also kind of a how fast do I like to ride. But for sure, it's the idea is, could we kind of, based on some desired speed estimate, calculate and desired power usage, kind of the power used for keeping your desired speed at the flat conditions, and then maybe there's a temporarily acceptable increase in power usage for the slope, but of course the length of the slope would probably also be important. But that's kind of where we are at the moment. And regarding the electric bikes, the last one, the Rumelastrand, I mean, the problem with this video-based measurements from the sky or from top is that you don't know what type of bike it is. So Guillermo also put some for short 4 hours. He had a camera on the side filming and then sitting manually and then annotating different types of bikes. At least for some of the tractors, we will know if it's electric, if it's kind of more racing, if it's a e-scooter, so some of that data. But that's on the flat segment, so of course it would be good to have it on the slope where we had the drone data. But in the end, it feels like you never have the data that you want. I don't know if you're feeling the same, but
yeah, familiar indeed.
Okay, thank you, Johan. I think we're right on time. So I'd just like to thank quickly Johan again for being here and for sharing your research with a very nice discussion. Thanks also to all of you for being present here and for keeping the session interactive. The recordings and the slides will be made available online on the TTS Lab website. So yeah, thank you. Have a good lunch. Hope to see you again in the next TTS Lab webinar. Okay, bye-bye.
Bye. Thanks for having me.
Thank you.
Bye.